going to do is kind of walk a very, very tight rope. Okay. So yesterday we did a lot of rheology, introduction to rheology. You kind of understand what is yield stress, what is viscosity, um, what causes a fluid to flow, what keeps it flowing. Remember all of those ideas, right? Starting to flow keeps it flowing. And then now we introduced in the morning, how does particles come in, and when you have aggregates and cement paste coating the aggregates, do all of that. Now we'll have to tie all of this together in some fashion to see how we can create a mix that is printable, right? So now, if I don't know any of this, if I have no idea about particle packing, if I have no idea about rheology, can I still print? What do you think? I completely refuse to come to this class. I don't care. It's so boring to sit inside and listen to all these people. I don't want this. I just want printing. Can you print? You can print without any control. You can print without any control. But can you gain control after printing a lot? You perhaps can. But then that will be shooting randomly, hoping that your bullet will hit the target once in a while, right? You will still win. Can still show your win. Look, I knew nothing about it. See what I printed. You might be able to do it, but that'll be once in a blue moon, only when all the stars align and not when your client and the customer wants. Correct? That's not what we want. So we want to kind of bring this understanding together so that again, even after that, like IS code says, like every code says, you have to do your trials and make sure that whatever adjustments you have to make, you will have to make. So I'm going to start putting in some theory behind all of these different disparate things. It's going to be a little wilder ride, so prepare for that at least until lunch. We're going to do multiple things. Okay, so going back to printing, if you have forgotten what that is from yesterday, you will have a pump that pumps the concrete that goes into the printer, and then you print it in whatever shape that you want, or you have a mixer and then you can directly put it in the printer. You can pump it whichever you want for using any of those materials. So this is your basic process that we start off again, and you can do all these different shapes. You can do structural and just refreshing what we did yesterday and today morning. So this is what we have in our plan of action. What do we need now? When you have a mixture that you need to print, and if you are printing through a nozzle, and if you're continuously printing a large amount of material, you need to pump your concrete through a pump to the nozzle, correct? You have to get to the nozzle. So your mix has to be pumpable. When the mix comes to the nozzle, it has to be extrudable through the nozzle, right? And once it is extruded, you have to be able to build it up, correct? In none of the, in your regular concrete, well, was it pumpable? Yeah, it's kind of pumpable. What do I do? It's not really pumpable the way I want. I add a little bit of admixture, add a little bit of water. That's fine. I make it pumpable. I got it. It's not really flowing. What do? I get my vibrator, vibrate the whole thing. I just want to fill the form. You have multiple levers that you can play. Your tolerances, your room for error is much higher. Right now, you have zero room for error. You are playing this very coordinated dance sequence where you see all these dance sequences where all the dancers do it in, otherwise it look very ugly, correct? Same thing. The first dancer, the pumpability dancer, will have to coordinate with the extrudability dancer and the buildability dancer to get what you want to effectively get. And this has to be coordinated. Easy? Great. It's great and easy if you're doing it in a computer and modeling this. Okay. If you actually start to do this, it starts to get more and more complicated. And that's where we need to have an understanding. Now, is an understanding guaranteed that you will get it? So I want to give you an example. So this is a social science research that they have done. Basically, what they did is to see how much of understanding versus practice balance is achievable. So what they did is they put 50 people in a room, right? From morning to evening, showed them videos where people are throwing darts. Right? You've seen throwing darts, right? In those circular things, and you have to throw in the bullseye. So the whole day they watched people throwing darts. By the evening, they gave them a questionnaire. And everybody said, no problem, we understand this, we can throw darts. Right? Because you've seen it the whole day. You think, okay, I understand it. I see the technique. I see them, how they put their hands, keep their hands, focus, concentration, watch it. I can do it. The next day, they take them to actually throw darts. Right? What percentage do you think even hit that outer circle? Less than 10%. So, have they understood it? Absolutely. Are you able to do it? The other example is I learned swimming through YouTube. Correct? Of course, yes, I know the technique well. Butterfly swimming, what does it mean? Jump at a certain angle, go into the water. That absolutely. You throw them in a river with YouTube. That's it. Right? You'll have 5 more people have to go and bring them out in a immobile fashion. So the understanding that you get, you might know all of this. Will you be able to do it? That's the thing. That's so in concrete technology, knowing is great. Being able to do it is a different thing, and that's why you will see a lot of people who know nothing about particle packing. I have seen actually people who can discern, who will see the aggregate, who will just walk into the ready mix plant, see the aggregate bins, walk around the aggregate bins, and tell the aggregate proportions. I've seen people who do that. Just looking at no sieve analysis, nothing, but they are not spring chicken like you. They are not 20 years old. They are 60, 70-year-old. Why? They have done this for 40 years, and at 40 years, they can do it. Right? What we are trying to do is shorten that span, get you to be able to do that in 10 or 15 years rather than 40 years, right? So that's where this whole thing comes in. So keep the right perspective. This is not going to make you solve all these problems tomorrow, but you will get an understanding. And once you do enough of it, you can accelerate the process of achieving the right results. This is not, you know, you're not going to solve all this tomorrow. 3 concrete mix designs doesn't make you a concrete rocket scientist. It'll take time. All right. So that's where we are going to go in. Printable mixes, we talked about that. You need to be able to print them up and build it. I talked about mortars plus aggregates, pre-placed aggregate concrete concept where you can build up things like this. You can do all these shapes. You can build up things in whatever fashion you want, depending on what materials you have. So here are a few things that we are trying to connect everything. So this slide, pay close attention. From whatever Dr. KBL has told this morning, plus what we heard yesterday, a lot of things are going to come here in one slide, and we will go in different directions in this slide as we go through. Okay, so what we want is we want things to be built up. Eventually, this is your aim, right? If I want a 1 meter column, I need to be able to build up a 1 meter column. This is your aim. In this, well, here is your extrusion process. Assuming that you have a pumpable mix, you have done all of that. You have an extrusion process. You want a certain viscosity. You know what the shear rate is. Shear rate comes from pumping, correct? And then the extrusion at the tip of the nozzle. You know what that value are. Hope that you have made a good estimate of that from your laboratory experiments. Does it make sense? Is that idea clear to all of you? Okay. Once having done that, what do I want to get it built up in time? With time, I want the stiffness to increase, not the strength. Of course, as stiffness increases, strength increases. But we don't want to be characterizing strength because at early ages, you can't calculate a strength. Right? You really cannot calculate a strength. Whatever, I mean, people will say, oh, this is a green strength. Yeah, for lack of anything else, and strength is what we love so much. Yes, it's okay. But what we actually want is a stiffness, because remember, in materials, if you're talking about solid mechanics, there are only two fundamental material properties. They are stiffness and Poisson's ratio, right? One is how stiff you get, which means what is the deformation for a certain stress in the direction of application of stress. And Poisson's ratio will tell you what is the elongation in the direction perpendicular to the application of stress. Those are just 2 points. And if you actually look at it, both of them are deformation criteria. They're not stress criteria at all. They're deformation criteria, right? And with 3D printing, what we want is to control deformations, which means it makes common sense to go through the deformation criteria. Does it make sense? Okay, so you want the modulus to go up with time. Now, I can have the modulus gradually increase with time like that. Is it enough for me? I want it to be quickly increasing with time. So, here is a concept that we are connecting from everything that we have heard so far. If I want modulus to be quickly increasing with time, what is the best way to do it? Okay, if you are talking about cement hydration, I can make the modulus go up as the cement gets more and more hydrated. Does it make sense? I increase the hydration of cement, which means I have one particle of cement, infinite amount of water around it. As this particle of cement hydrates, my stiffness will increase, correct? But then that's a slow process. So what I want is already set the system up in a way that can get a quick modulus. What is it? How can it be? So I have one particle here, one particle here. The combined modulus should increase faster. What do? The glue should happen faster. Make sense? Which means I need to make sure that the particles are packed well enough so that the cement paste around it quickly hydrates and creates network so that the combined modulus of the system goes up higher. Is it clear? You see the importance of particle packing? The particles have to be packed well. So that is what you want to get the modulus higher. And then once you get the modulus, of course, you have shear stresses that are happening. You want it to be built up in a way so that you don't have off-axis stresses building up and causing buckling failures, off-axis failures like that. So that's what you want. Now, if you look at a mix, so in this is yield stress, that is plastic viscosity. I'm just using these two parameters because yesterday we learned to measure these two. Yes. Stiffness, elastic modulus. Okay. The reason I did not say any other modulus is if you're measuring a shear stress, I can't tell you that's not important. Then it becomes shear modulus. If it's shear strain, shear modulus. But if I'm building it up, I'm thinking about axial stresses and axial strains. Now, you can always ask, is shear not important? Or won't I do off-axis failure? Yes. If that's the case, shear modulus. But if you know elastic modulus, can't you calculate shear modulus if you know Poisson's ratio? Straightforward, they are linear relations, right? So that's a straightforward relationship. And that's why I said modulus. If it is axial strain, elastic modulus. If it is shear strain, shear modulus. All right, so these are the two terms that we learned yesterday, correct? These are the two, yield stress and plastic viscosity. Now, I put in a big band of where I can live. So if I have an extremely high yield stress with a very low viscosity, I know I can't print it, I can't extrude it, right? So forget it. If I have an extremely high viscosity with a low yield stress, yeah, I can really pump it, but I can't build it up, which means those are out of the picture. I kind of come up with a band like this. Now, within this band, what do I want? If I have a low yield stress with whatever plastic viscosity that I can consider, low yield stress, which means a highly flowable fluid, correct? Yield stress is that stress that is required to initiate flow. Lower that value, faster it will flow, correct? Right? Which means that's where it is. Okay. Can I build that up then? It'll flow faster. Can I keep building up layers? Probably not. Minimal buildability at that state. Now, if I increase the yield stress a little bit more, I can start to make it much more buildable. I now want to introduce to you one more concept which we have not really covered, but I'm sure you are able to extrapolate from what we have learned. If yield stress is that stress which is required to initiate flow, that's what we also saw that, right? Because you have that yield stress and then beyond that the flow starts. If yield stress is that which is required to initiate flow, we also talked about the idea that that is what is required to break that network. Break the network of particles so that it will start to flow. So, which breaking the network meaning what? Removing the contacts between particles, because it is the particle contacts that create shear stresses. This movement between particles is restricted by those contacts, correct? So if I start to break the contacts, if I start to move particle contacts away, which means automatically lowering the yield stress. Everybody good with that? So I want to get to a point where I want to break that particles with the bond between particles. So I want to get to a point where the mix is not too stiff, yield stress is not very high. The mix is not too wet, viscosity is not very high. I want to be in a zone where there is enough yield stress and there is enough viscosity. There is enough yield stress to initiate flow. There is enough viscosity to keep flowing. Correct? So that is your impossible condition that we have to satisfy. Not impossible, we can. So that's the intermediate buildability condition. Now, if I have an intermediate buildability, yes, I have my yield stress and plastic viscosity controlled in such a way that I can start building it up. But then once it gets to a certain height, the yield stress is not high enough to hold the layers that are below. Right? There is not enough stiffness to hold the layers below. Intermediate buildability. What I want then? I want it to go higher yield stress. Now, I can increase the yield stress higher and I can increase buildability as much as possible. But what is the downside of increasing yield stress? Hmm? Which you need more force to initiate flow. So yield stress increasing after I build the layer is great, but yield stress higher at the moment of extrusion is not very good. The fact that you can do is you can make the mix in such a way that you can add admixtures, delay the open time, do all of that. But all of those gets very complicated, as you can see from this picture. And this tells you only half the story. Yield stress is not the only thing. You have other parameters also, which we will talk about. And then as you get to a higher place, this blue zone is actually a good zone. A certain yield stress with a certain viscosity will get you good enough buildability with delayed collapse, good enough buildability and extrudability. But you further increase the yield stress, your material will get stuck in the nozzle. So this picture, try to keep it in your mind. Now, what does materials do in this whole thing? No, if you have a certain yield stress and plastic viscosity, you add superplasticizer. Dr. Subbu said this earlier. Superplasticizer is supposed to lower the yield stress and not the viscosity. You see that in that picture there? You're lowering the yield stress. You're not supposed to. Superplasticizers are not supposed to do anything to the viscosity, because superplasticizers by nature does nothing but to separate the cement grains farther apart. They do nothing but deflocculate the cement grains. They do not add extra water to the system. They cannot bring in more viscosity in any form or fashion. If you have to change the viscosity, you have to add a viscosity modifying admixture that changes the viscosity of the solution, that changes water to honey or honey to oil or whatever, right? Otherwise, superplasticizer simply spreads the cement paste farther apart, giving you an illusion that this is actually flowing better. By spreading these particles farther apart, what are they doing? These two cement paste particles are sitting like this. Superplasticizers, because of this phenomena called steric hindrance, some of you would have heard in your classes. Steric hindrance simply breaks this apart. They just go away, which means the contacts are broken. When the contacts are broken, yield stress comes down because you've broken the network. That's all what you have done. Silica fume. Now you add silica fume, what happens? Why am I doing this? When you add silica fume, what happens? For a certain dosage, you might see viscosity dropping a little bit, right? You will see the flow becoming easier because silica fume particles accelerate the flow at very low dose of 1%, 2%. But when you get to 3, 4, 5%, they do the opposite effect. They start to collect all these particles together, start to clump. You will need more admixture. So depending on what you want with yield stress, you can play around with silica fume. Water, of course, you don't want to do this, but that's what water will do. You don't want to add extra water for all the reasons that you know. And of course, aggregates, depending on what you have, does all of this. So what is printability? Printability is buildability plus or extrudability plus buildability. You should be able to extrude through the nozzle and build up layer by layer. What do we need for that? Everything that we have talked about earlier, right? You need the paste to have the ideal yield stress and plastic viscosity. You need the aggregates if you are having aggregates to be able to be spaced and particles to be packed in such a fashion that you give stiffness to the system, and then you should be able to print it, and then you should be able to build it up well. We talked about coating thickness when we talked about paste thickness. You can find the coating thickness based on simple fluid mechanics equations that uses viscosity, density, the particle sizes, the velocity of flow, all of that. You can find the ideal coating thickness for different applications. We'll work on that a little later. Now, you have pretty much to get a good yield stress and plastic viscosity that you want to flow, you want a certain amount of paste coating the aggregates, right? And that's what you heard in the morning. Your codes will do all of that empirically. By specifying the minimum cement content for workability and a minimum or maximum water cement ratio, they are simply specifying a certain paste volume. And depending on your aggregate sizes, you can find out based on surface area what is the thickness of the paste. So what you're doing is a paste thickness, and here is a relationship between yield stress and the excess paste volume. As the excess paste volume increases, as you increase the dynamic yield stress of the paste, that is an indication that you have excess paste volume. So again, mixed design will also have to account for the fact that how much of paste volume you have in excess than what you want to coat the surface of aggregates. Because any excess paste is wasted opportunity, is wasted resources, is wasted money. So if you want to mix optimization, that's what you do. Okay, we talked about conflicting demands about stiffness and flowability. Again, stiffness or modulus. You want the modulus to be higher and higher and developing fast so that you can build up your layers and you can build the stuff faster. One of the biggest advantages of 3D printing, if you look at people who are touting this technology, will say that, oh, you can do very fast construction, correct? If you want fast construction, you better build things up fast. And if you want to have better buildability, you want the material to develop its stiffness faster. Not stiffness while it is sitting in the mix and the nozzle, but stiffness after it has come out of the extruder. So that's what you want. But in the extruder, you want better flowability so that you can get a cohesive mix that's coming out. So, this one that you see here is good. This one, very good. So this is very nice and pumpable. But what happens with buildability? Nothing. It's extrudable. It beautifully, nicely extrudes. You'll be very happy to extrude it. But then if somebody wants, can you extrude the shape? You will say, you know what, whatever shape comes out is the shape that you should buy. That's not probably going to work. This is fairly good. You can do whatever you want. This one, lots of people are putting in lots of effort and struggling to get it out in some fashion. Finally, if you give the product something like this, of course, you've lost your money. And this one, of course, it is not even extruding, right? It extrudes whenever the extruder thinks it wants to extrude. You're not getting a continuous extrusion. So you have the whole variety of this, and if this is what you want, this is probably that conflicting stiffness and flowability demand that you want to satisfy. Okay, so how does rheology and packing build into all of this? Now, in the evening session on today, we'll do a demonstration and you will be able to play around with a few things. We'll do packing. Again, the software is not as complete as I would have wanted it to be, but it is in a shape where you can actually pack particles. You can visualize the packing of particles. Avinay is going to give you a bunch of data sheets with different size distributions that you can play around and see how it packs. And then there are calculations that I'll show, which eventually these people, they have promised me that they'll get this app working and running soon. And we will send it to you because all your emails are there. We'll send it to you so that you can download it and play around and know all the particle packing characteristics. You can do all of that. So eventually, we hope we'll get you there. So you have all these mixes, and all these materials have different size distributions, right? Cement and fly ash and limestone all have different particle size distributions. You can have then different workability based on this. They'll have all different packing you can do. So you can optimize the proportions for maximum packing, optimize the proportions for the flowability and the extrudability that you want. And then these two requirements you can match in some fashion. And, we haven't really done it specifically for 3D printed mixes, but we have done it for UHPCs in a complete fashion and published to get rheology and packing based complete mixture design criteria, because UHPC's mixture design is more of a straightforward way of doing it compared to 3D printing, but the same principles will apply. Now, binder type. So if you want to start with packing, you talk about binders. What type of binders, right? So it'll be a good time to talk about binders that you will use. Most of the time, your 3D printed concrete will have a high binder content, correct? You are talking about 800 to 1,000 kilograms per meter cube of cement. Extremely high value. You don't really have to do that. You can drop it by 50% straight away. You can get to about 50% replacement of cement with some other materials if you know the way to control particle packing and rheology, right? So a few things that'll be handy. And let's do some thought exercises here. I give you a bunch of different cement replacements. Let's assume that you have all the cement replacement materials that you commonly have, okay? And if I tell you, you can't change the water content in your mix, but I want the yield stress to be dropped. I want a lower yield stress. Your water content has to be the same. I want a lower yield stress. I'm giving you cement, fly ash, silica fume, slag. What material will you use? Flash. Why? Assuming that particle sizes are in the general range of cement, they're not extremely fine, not extremely coarse. Why fly ash? What will the shape do? Spherical shape, what will it do? Let's talk in terms of what we have been hearing yesterday and today. In terms of, so what is yield stress? It is a stress that is required to be overcome to initiate the flow. What will fly ash do? What will a spherical particle do to initiate flow? It will reduce the friction between particles. The smoother particles, the ball bearing effect will start to make it flow, roll better. The resistance to flow is lowered. Fly ash will do a good job. So given a certain yield stress that you have to achieve to get there, by replacing cement, fly ash is a good option, correct? Now, what if I want to increase the yield stress? I accidentally added quite an extra amount of fly ash. Now, I want to increase the yield stress. What particle will you add now to increase the yield stress? Slag, maybe. Why slag? Very angular particles, right? So it might be beneficial, but its angularity is very comparable to cement. So it's not going to really do too much different from what cement does. What's your next option? I can add aggregates. Yes, if I want, I might add some sand. I might add some angular coarser particles, right? So I might make it into a mortar to get your slightly higher yield stress. Okay. Now, if I want to control viscosity, what are my options? Does any of these particles change the viscosity? No. Right? Does admixtures change viscosity? Yes. Which admixture will change it? A viscosity modifying admixture will change the viscosity. So if I have to really change the viscosity, and that's why a lot of 3D printed mixers, you will see people using viscosity modifying admixtures because they have to control the viscosity in some fashion, right? Yield stress, you can play around with particles nicely. Viscosity, you have to use a viscosity modifying admixture. So now you have all these different options that you can play around. So you reduce the cement content, you can play around with all of these. And with strength, when you replace a certain amount of cement with some other materials, will you lose strength or will you gain strength? Whatever answer you're going to say is going to be right and wrong, correct? Yeah, that's how it is. You will say that fly ash, then you can ask me at what age? How much of fly ash? Are you reducing the water? You can ask all these questions. But generally, if I simply replace cement with fly ash, at 28 days, what will happen? Generally, I will have lower strength. So what do I do to control that? I don't want a lower strength. What do I do? Water to cement ratio, but we have to look at water to cement ratio slightly differently here. Right? Don't say I will reduce the water cement ratio. You can say that I will increase the particle density, right? Because particle density, your yield stress is what you want to maintain to make it extrudable and buildable. What you want are particle contacts. I want now to play around with the different sizes of particles, and that's where limestone powder is suddenly a wonderful additive for 3D printed concrete. You will get, because of its finer particle sizes, the ability to get it in different particle sizes that you want, and the fact that it really doesn't interfere much with cement hydration. It'll stay as a filler, it'll do some fine filler effect. You can start to play around with particles. So really the idea is that using binders. Now I've put in metakaolin also. Really don't try a clay-based material in printing unless you really love clays and you have designed the mix for an LC3 or a clay-like mixer. Otherwise, the cohesiveness of that will make extrudability a really, really difficult task. It's not that's not possible. The water demand also is going to be very high. When the water demand goes very high, you will either have to use lots of admixtures or lots of water. Both are not good. Lots of water not good for strength. Lots of admixture not good for economy of your mix. So again, few things to remember when you look at all those binder types. Now, coarse aggregates incorporation. You can incorporate coarse aggregates. When they say coarse aggregates, it's typically less than 10 millimeters, right? You're not talking about 1-inch aggregates. No, none of that. Less than 9.5 mm aggregates. And so there's a certain zone in which you have a coarse to fine aggregate ratio that you can print, which is a function of your mix optimization, particle size, and all of that. And you can look at that. Now, if I'm really looking at particles, and this is more of a fundamental material science ideas, what are the factors that I have to look when you pack particles? So I'm sure you have seen in one of your basic material science classes particle packing ideas, right? Simple cube, body-centered cube, face-centered cube. All of you have done that, right? A body-centered cube, for example, has a packing factor of 0.68. Face-centered cube has 0.74. Face-centered cube is or a hexagonal closed packing, which is another form similar to face-centered cube. Hexagonal closed packing or face-centered cube both have an atomic packing or a packing ratio of 0.74, which means if I take a box and take same size spheres and I pack them in the form of a hexagonal closed packing or a face-centered cube, I can pack 74% of the volume of the cube with these particles. The remaining 26% will be empty. So if I have only spherical particles, which is what we will do to idealize like you've seen in the morning, if I have only those spherical particles, what do I need to increase my packing fraction? I need to add smaller particles. If you keep on adding smaller and smaller and smaller particles, you can get to 0.905. That is a theoretical absolute maximum gymnastic particle volume fraction that you can get. 0.905 is what you can get by packing all these particles different size particles, right? But those are spherical particles. That's what you get. When you pack those particles now, if you have, say, cement, fly ash, silica fume, limestone, different types of particles with different size fractions, right? Then the nearest neighbors are going to be different. Hydration changes when the nearest neighbors are different, right? So when you have a limestone as fine filler, when you have a filler effect that is happening, and when you want these fine fillers to do nucleation, you want them to be distributed as much as possible, closer to cement, high cement particles to hydrate and all of that. So you can do a few of these microstructural terms: number density, coordination number, and mean centroidal distance. Number density is the number of particles per unit volume. As the size goes down, number density goes up. Correct? So you can do a certain number density. Coordination number, number of nearest neighbors within a certain distance from a particle, which means if I take a cement particle, how many nearest neighbors do I have? And who are my nearest neighbors? Right? If my cement particle has all the nearest neighbors on reactive particles, then my cement has to work hard in that area to do it, right? So how do we distribute those particles? And then mean centroidal distance is distance from the surface of a particle to the surface of its nearest particle. Again, these are all mostly for control, hydration control, but we can use it for packing aspects as well. So here is plain OPCs. I want you to look at this carefully. This is just the particle size distribution of plain cement. So all the different particles. I throw in a few more limestone into cement, right? 70% cement, 30% limestone. All these blue particles are limestone, and limestone has smaller size distribution than cement. What happens to the packing density of this system compared to this? It's definitely going to be higher. Here is a system with 70% cement, 15% silica fume, and 15% limestone. Silica fume is even finer than limestone. What happens to the packing density of this system? Even finer, even higher, most closely packed than this, right? And you see here, what have I done? If you simply look at the cement grains, I have spread the cement grains farther apart. I have reduced the amount of cement in the system. Why is it important to reduce the amount of cement in the system? It'll be cheaper, but think about 3D printing. When you're 3D printing a wall with extremely high exposed area with a large amount of cement, what are you going to get? Higher shrinkage cracking, correct? You're going to get one of the most important problems with 3D printing is shrinkage cracking, which we will see later. So to control shrinkage cracking, your best possible option is to control the amount of cement, which means you have to fill it with some other particles, maintaining your extrudability and buildability at the same level. And here is what's packing in a unit volume in 3 dimensions. You will see all of this in the evening, I hope. Okay, now let's get to the aggregate story a little bit. And here is where I want it to be, you to understand. You've seen this in the morning slide also. Here is packing density. Here is a fraction of aggregates. Remember, in the morning presentation, what Shubhu showed, this graph was like this. You saw that? This is, oops. This is packing density. What he was showing was a volume of voids, which is 1 minus packing density. So this graph was like this. And you said there was a minimum value where the voids are minimum. The same thing I'm saying, like a minimum value where voids are minimum, I'm saying there is a maximum value for packing density. The same thing for a certain combination of aggregates. How do you get that is the whole idea of doing packing. Okay, so here are some packing parameters. We'll come back to that later. You've seen this picture earlier also in the morning, in slightly different form. So when I have all similar size particles with one particle that's trying to go in, it tries to loosen the system, right? So if you try to put in certain amount of sand into aggregates, it's actually initially loosening it before you start to fill that thing back up. So there's something called loosening effect where a smaller particle goes into, again, this is the same thing that happens in crystals when you have defects. It's called substitutional defects. For example, if you make steel from iron and carbon. Iron is a vacancy defect that steel is, sorry, carbon is a vacancy defect that goes to the crystal structure of iron, changes the crystal structure of iron. So if you remember your steel phase diagram, I'm sure you won't have to remember it, but if you remember it, you will know that steel, pure iron at room temperature, it is a body-centered cubic crystal structure. If you simply heat pure iron to get to 700 degrees Celsius, close to 700 degrees Celsius, BCC changes to an FCC structure. Simply by heating, your crystal structure changes. FCC has a higher packing than BCC. Now you heat even further, the atoms, particles rearrange, reorganize, you get back a BCC structure, right? So lots of these metals do that through temperature changes. And when you add carbon in, carbon is an interstitial impurity in iron. When you add carbon in to create steel, you change the crystal structure in so many different ways. You change the packing of the iron crystals, Fe crystals. So that's very similarly, you have loosening effect. Now, if you have something that is all these small particles lining along close to a large particles, there is a wall effect. You remember interfacial transition zone in your cement hydration story? That's a wall effect basically. Calcium hydroxide sticking along the aggregate particles and forming a zone of higher porosity because you really can't fill things along a boundary well. That's wall effect. You see that with aggregates as well. And then you have wedging effect, right? This guy trying to squeeze in through and create more distances. And as an function of interparticle interaction, loosening effect and wall effect creates reduction in particle density or packing density. This is what happens. Again, these are all simulated values that we have done. Okay. Remember this picture yesterday? How does this relate now? What was this? Viscosity as a function of volume fraction and sizes. So yesterday I told you we are going to get back here when we talk about packing. So here is as a function of sizes. So smaller spheres, you get larger viscosity. Larger spheres, you get larger viscosity. Somewhere in the middle, you have a lower viscosity, faster, easier flow. So it's not just one size that does it, it's a combination of sizes that does it. And again, here we saw that when you increase the shear rate, you kind of take away the particle effect. I'll come back to this later. That is, so I'll do this compressible packing model, very similar to the packing that you have heard in the morning. We are going to throw in a little bit more of mathematics into it. There are several different models for packing. You can have monodisperse, polydisperse. You can have packing that's based on only packing densities, packing that's based on size and density, so many different varieties. But this is one kind of a packing model that is computationally more easier to implement. And that's why I do it, so that when I give you the app finally for particle packing, it'll have this model. So what it does is to take into account what's called a compaction index, which is simply a number, a scalar number, which depends on size distribution of aggregates that facilitate better packing and the effort involved in packing. Right now, you pack particles, it doesn't come free, it comes with expense of energy. If you want to pack something more into a system, you have to give it energy, correct? You have to vibrate it, you have to rod it, you have to compact it, something, correct? Just by taking a bunch of particles and putting in a volume, will it compact well? You have to vibrate it, you have to let it go into the right spaces to fill it, correct? Same thing with the concrete also. You vibrate your concrete to get it a better density. So you need to provide energy. So this K is an indication of both the distribution of particle sizes and the energy that you give. And through experiments, they have come up with lots of those numbers. You can use a value of 9 for extremely well-packed particles. 9 is a good number for extremely well-packed particles, irrespective of the size of the particles. If you don't want extreme well-packing, for example, if you're doing pervious concrete, all of you have heard about pervious concrete? Very loosely packed systems. You do a number like 5 or 6. right? So again, this is not for concrete alone. You can use it for any um, multi-size particle system. Okay. Now, in that, you have a few terms. Here, you have y sub I represents the individual packing fractions of the aggregate. So, assume that I have number 8, number 4, 3/8, half an inch, all different size of aggregates. I sieve them separately. Assume that I have sieved them separately and put 4 different clusters. Now, typically, what you have in a ready-mix concrete plant are at least 2 different coarse aggregate gradations. Have you guys gone and seen a ready-mix concrete plant? And if this, have you seen their aggregate piles? You have at least 2 aggregate piles, if not more. If you're doing much more controlled concrete mixtures, if you're doing UHPCs, you may have 4 or 5 different bins. Otherwise, you'll have 2 different size bins corresponding to 2 different sizes, and you have a fine aggregate bin as well. So if you use different aggregate sizes, y sub I represents individual packing fraction of the aggregate. What do I mean by that? If I take number 4 aggregates alone, now when you sieve those aggregates, what does number 4 aggregate mean? All of you have done some sieving of aggregates at some point of time? What does number 4 mean or number 8 mean? Those are the nominal maximum size of the, that's what you say, right? In mixed design, nominal maximum aggregate size. What does a nominal maximum aggregate size mean? A nominal maximum aggregate size of number 4 is everything that is passing the sieve right above but retained on that sieve, correct? So if I have that alone, I will have a size of different size distribution even within that nominal maximum size, correct? So if I take all of that and do a maximum packing. Now, have you done a maximum packing? You probably have done in your soil mechanics class where you tamp the soil to get the density of soils. Same idea in concrete also, in aggregates also, you would have done it. You can take the aggregates, put it in a vessel, put it in 3 layers, tamp it 25 times each layer, and find the weight of it, and based on that, find out what's the maximum packing that you can do in a certain volume. Have you done that? Guys, kind of get the idea of what I'm trying to say? So you find individual packing density. So if I take a well-rounded, really rounded aggregates, and I try to pack a volume, assume that's number 4 aggregates, really, really rounded for argument's sake. Okay, I'm trying to pack into a cylinder, number 4 aggregates. How much can I expect my maximum packing density to be? I gave you the number a little earlier. 0 point? No, this is number 4 alone. 0.74 maximum, right? So if you do the experiment and get the answer as 0.78, you better go back and redo the experiment. You're wrong. It clearly says you're wrong. Unless the aggregate is really angular and has all of that. But generally, you know what kind of upper limit that you're looking for, correct? So you find the maximum. Now, if I go to number 8 and do the same experiment, what's the maximum number I could expect? Same, right? Because number 8, it's only the size that has changed. The shape is still the same size. So you get 0.74 is a maximum that you can get. You typically will get 0.65, 0.66. Generally, if you do aggregates, that's what you get. So y sub I is all of those values. If I'm using 3 different aggregates, y sub I is y1, y2, y3. Good. Beta I is a residual packing density, which is the packing density of a mixture consisting of only the aggregate class I, which is your dry roded unit weight. You can use a dry roded unit weight for that class of aggregates. And virtual packing density, gamma I, is a theoretical packing density. When class I is dominant, there are ways in which you can do a theoretical packing density. You can either do it computationally or you can do it through a series of experiments and minimize the results of all the experiments. So this involves quite a few experiments to do. And then you get you can solve this. So this is gamma I, which is beta I over this big function where Aij and Bij are the loosening effect, wall effect, and the effect of fibers and all of that. You can use based on the aggregate sizes, you can get the loosening effect, the wall effect. So that gives you gamma I. And then you can use an optimization method, a Newton-Raphson method, for example, for those who have done a numerical methods class. You can use that to optimize the value for and find the value of gamma I based on this. And then if you have fibers in it, your fibers will also perturb the volume. Fibers are long. They'll also try to move the materials farther apart. You can account for the perturbation volume. All of it said and done. Here is, so if I'm using, these are the different aggregate sizes, 1, 2, 3, 4 different aggregates, sand, fibers, all of that. So here is your simulated model. Again, I'll eventually give you, I promise, in the next month, the software that will do all of this for you free. So this is what you take the volume fraction of coarse aggregates and you start doing whatever fraction of, so this is about 800 simulations of so many different combinations. Okay, no experiments, simply your software will do it. And then I will do the theoretical pack density. You see, at about 0.6% volume fraction of coarse aggregate, I get my maximum packing density of aggregates. Maximum packing density of aggregates about 0.72 or so, which means I can make a system with 28% paste. You see that? That's your minimum paste content that I want to pack the system. Similarly, for a different size distribution, my maximum volume fraction slightly changes. And then my experimental versus predicted to show that my model is good. So this is your packing density calculation using what's called the compressible packing model. Exactly based on theory of how particles pack. And if I do some examples based on 3 different sizes, a fine, intermediate, and coarse aggregates, increasing packing density from 0.65 to 0.82. What does this point? So among this, do you think which one will have a 0.82? Oops. Fine, intermediate, or coarse? Which one will have a? Don't try and say an answer quickly. If no answer is also a good answer, right? The idea is to identify at what time there is no answer also. Can I say among this one, which is the one that is 0.65, which is the one that's 0.82? Yes or no? I don't know any other information. I say coarse, intermediate, fine. So one is very coarse, one is very fine, the other is in between sizes. I can't, right? It could be either one, it could be anyone. I don't know. It could be depending on what do you mean by intermediate? How many sieve ranges have I covered in the intermediate, correct? Now, likely you can make an educated guess and say this 0.82 consists of a larger size range. That you can say, correct? Because if it's only one size, I should be closer to 0.74. Because I have a higher value that I experimentally determined, one, you can simply tell the guy you're wrong, right? But telling somebody that he's wrong without proof also is not a good thing. But then you can say that maybe that range has a larger sizes included. You get the idea? So you between 0.65 and 0.82, and I do a lot of simulations, a lot of experiments here, and I say that's my optimal value, which is 0.7, 0.80785 or something, and then 0.79 is what I get using the compressible packing model. So the model actually does pretty well for lots of different things. All right. So that's the idea of particle packing, which we will come back again when we talk about extrudability and buildability. Should we stop now or coffee break? We can stop, right? All right. So we'll stop now. Oh, any questions? Or we'll come back and do some questions then, because I'm not going to get through what I'm supposed to get through until lunch. So we'll do some questions and we'll stop somewhere in the middle. Okay. So we'll have a longer day today. We'll leave you only Only long later. No. They have to sit and pretend to be awake. I have to sit and pretend to be. I'm not going to get it. So let's break a couple copies. Everybody here? Okay. So continuing from where we left, we're talking about packing effects, how that affects rheological properties, and how eventually, we haven't seen that yet, but how eventually we will see how all of this will affect extrudability and buildability, which is basically your printability criteria. Yield stress and slump, you heard this in the morning. Yield stress is an indicator, or slump is an indicator of yield stress. So for different materials, if you look at yield stress as you add more and more materials, again, many of the concepts we talked about, you can see here, right? If I add 30% of limestone and replace cement with that, and limestone is much finer than cement, see my yield stress increases, right? Why? The number of particle contacts have gone up. As I go with smaller and smaller sizes, the number of particle contacts have gone up, yield stress has gone up. Similarly, so everything on the right side of OPC here are systems where cement has been replaced with particles of smaller sizes, right? And then with metakaolin, you'll see the yield stress really, really going up. Why? Not just particle size effect, but also the effect of clay, which has the ability to hold on to the water and not allow water to the rest of the mix so that it'll become much stiffer. So with metakaolin, that's what you see. With all these mixes, all of these ones, which it is simply the effect of the more number of particles, more number of particle contacts, more energy required to break the flocks, more stress required to break the flocks. Correct? That's what you're seeing. And then if you do yield stress as a very quick and slump as a very quick measure of can I print or not, this is what you get. At very low yield stresses, you really can't print. But at lower slump values and higher yield stress, you get some stable printed shapes. Again, trial and error way that you can get it, and you can relate yield stress to slump. Packing and printability, going back to the same idea, how do we now start to quantify packing and printability effects? So here are a few printable mixes. Again, the idea being that OPC with some other replacement of materials to get you better buildability, better shape stability, and all of that. There are now 3D printing systems that are called 2K systems. So 1K system is basically your pump and one extruder. You extrude that one material. Now we have 2K systems that will allow you addition of accelerators or whatever admixtures just before the nozzle. Right? So why do you need that? You want it to be extrudable. For that, you want a low enough yield stress so that it's extrudable, but then you add an accelerating admixture at the tip of the extruder nozzle so that when it comes out, it'll become quickly buildable. The yield stress goes up because the accelerator accelerates cement hydration. Remember I told you, if I have two particles and cement grains in between, the one way to increase the yield stress is to get acceleration of hydration, get more hydrated products formed, correct? Replace the water with more of hydrated products, correct? So you get, again, remember, for any unit volume of cement that you take, or cement when you start before hydration, after hydration, you get twice the volume roughly, correct? All of you know that, right? A unit volume of cement hydrates to twice its volume when hydrated completely. It's not hydrating completely here, but you see how the volume has increased. That increased volume fills up the space, increases the stiffness, and be able to hold the shape much better. So that's the benefit of adding an accelerator at the tip of the nozzle just before it comes out. You don't want to do it ahead of time. You don't want to do it while the material is within the extruder, because it'll get stuck in the extruder. Addition of reinforcement. Again, a material design of 3D printing has a lot to do with fiber reinforcement, not because we can't print without fibers. We can absolutely print without fibers, but the fact that we have no other really credible way of reinforcing this material. So, is there a better way that we can at least get some tensile strength built into your printed material? So, fibers are added. And if you look at random shape of fibers added, you get through it. You see these fibers aligning along the direction of printing. The fibers will start to align along the direction of printing. So when you print a layer, you will have short fibers aligned along the direction of printing. Like we talked about yesterday, you're now getting an anisotropic composite material. The concrete does not have same properties in all the different directions. Depending on the direction of testing, your properties are going to be different. Not much in the compressive property part with fibers, but with respect to tensile properties, flexural and tensile properties, which is something that we need to think about. Types of fibers, you have lots of different types of fibers that you can use: aramid, glass, textile, cellulose, polypropylene, lots of different fibers. Effect depends on the type of fiber, quantity of fiber, aspect ratio, which is length to the least lateral dimension of the fiber. Print parameters selected: how quickly you're printing, how many layers you're printing up, all of that. And then the material composition. So again, fibers, we'll see more of that when we talk about mechanical properties, but fibers also influence the properties. In the fresh state, fibers influence workability. All of you know that, right? When you add fibers, workability is influenced. Changes yield stress, changes cohesiveness, shrinkage, cracking, surface finish. All of those properties are changed by fibers. And if you have an improper mixed design, you will have settling of fibers, improper bond, stiff mixtures where you can't print, etc. Printing fiber reinforced mixes, just to give you a few examples. Um, Remember the wall effect that you saw with aggregates, where things will get stuck onto the wall and create a different packing closer to the wall? Same thing here also. You will have fibers there, and in between you will have fibers all randomly aligned, and then depending on the size and the effect. But as you come through the nozzle, effectively, if the fiber dimension is anyway close to the size of the nozzle, you will have aligned fibers. If the fiber is extremely small as compared to the nozzle size, you will still get random orientation. In regular concrete, when you throw in fibers, you are relying on a random orientation, correct? You expect the fibers to be randomly oriented so that your concrete gets the properties equally in all three directions. So here are some examples of fiber effects on the hardened state. Compressive strength, flexural strength. You can see that, and we'll talk about some of these things as we go through. Plain versus fiber reinforced. Compression, really fibers don't do much in compression at really small volumes. Very high volumes when we use UHPCs, ultra high performance concretes, where up to 3% by volume of fibers are used. Then you will start to see increase in strength. This is about 0.3%. You will see almost no effect in compression, but you will see effects in tension and flexure. In the hardened state, again, you see here fiber dispersion of how the fibers are dispersed in the, so when you're testing in flexure, how the fibers are distributed. So if your fibers are in this direction and you are bending it in this direction, these fibers arrest the cracks, and therefore the flexural strength will be higher. Whereas if you are in this direction, cracks can really go in between fibers, right? So you really have no increase in strength. Again, out of the fiber, which is good for tensile strength. Steel fibers, obviously, right? Steel is, because steel has better tensile properties, it'll be better. If you want crack reduction or load, polypropylene is perhaps good. But aramid fibers are also very good, very stiff fibers, but they're much more expensive. But steel is perhaps the best and most commonly used, so you can use it evenly. So again, for flexure, if you have a beam that you're testing in flexure, and if your fibers all aligned in this direction, a crack that is going in this direction, assume that you have a beam like that, a crack that's going in this direction will find a fiber, and you'll find all the effects associated with fibers, crack blending, crack deflection, all of that, and therefore the toughness will increase, the flexural strength will increase. Whereas if you print it in such a way that fibers are aligned like this, a crack can go right here. You might not see any influence of fibers at all. If you have normal kind of casting of concrete, you expect the fibers to be in all different orientations possible, all different directions possible, which means statistically there is a chance of finding a fiber everywhere, and that's why the properties are increased. In this case, the properties are much more increased because you're absolutely certain to find a fiber on the path if you have fibers aligned in that direction. So everybody gets the difference, right? So printing direction matters. This is simply to say that printing direction matters. How you print, what direction you print matters with respect to testing. Now, if you print a slab and cut a piece of beam to test, the direction of testing matters. So when you say that I got so and so flexural strength when I used fibers in my 3D printed mixture, what you have to specify absolutely is what was the direction of testing. Because you're dealing with now an anisotropic composite. Any of you who have taken continuum mechanics stress analysis class will know that now your stress tensor will have 9 components. We simplify to 3 components. If you have x, y, z directions and you do sigma 1, sigma 2, sigma 3, now you will have 1, 1, 1, 2, 1, 3, 2, 1, 2, 2. You'll have all those 9 components. So make sure that that will have to be accounted for. Of course, you can remove a few of those because they'll be very similar, but generally it'll be what is called an anisotropic composite. Target demands in what we want, again, things that we have talked about earlier. Rheology, important. We talked a lot about rheology. Extrudability, we are starting to talk some of that. Stability, we need it to be stable. How much time? All of those, there is viscosity, there is static yield stress, there is dynamic yield stress. All of those will have to be accounted for in some fashion. Now, will we be able to account for everything all the time? No. But like every good optimization, you should get 2 of the 3 correct. Right? One of the 3 probably won't work. None of the 3 absolutely is a disaster. But at least 2 of the 3 parameters that you want, you should work, and you should be able to pick up which one you want. So if I'm just looking at a simple, there's a very, very simple conceptual diagram to show, because right now, you know only about yield stress and viscosity, correct? That's what the rheology that you know. You know static yield stress, you know dynamic yield stress, you know viscosity. What is that printable region in which this works? And this will in turn help you to find what is that mix that satisfies these given criteria. So if you are doing 3D printing, like many of these ready mix companies, if you ask for an M30 mix, they will have a standard M30 mix. When you go and ask for an M30 concrete, the guy is not sitting there and starting to proportion M30 concrete. They have an M30 concrete ready based on the cement that they use, the aggregate sources that they have, all the conditions that they have an M30 concrete optimized and ready to go. So next time you go on M30 concrete, they have it. They'll have M35, they have M40. Only time they may have to do a new one is when you ask for an M100. Because nobody asks for it all the time, then they'll have to design it. Similarly, if you are in the process of printing concrete regularly, if you want to print a complete house or a complete building, you will have that mix ready, and this will be a good place to select what that mix would be. And of course, you would tweak accordingly. Today is 40 degrees, tomorrow is going to be 30 degrees. You will adjust the parameters accordingly. As a concrete engineer, you would know how to do that, right? The admixture dosages, the cementitious content. You will adjust things a little bit here and there, but you will have some kind of a standard recipe. Like restaurants, right? You go there, they have, I mean, not that when you order, they'll have 200 things in the menu, but really there are no 200 things, right? They have a bunch of standard things that they mix. Similarly, as an engineer, you have some of those standard things, all based on what parameters you choose to control, what parameters you choose to test regularly. The reason why viscosity and yield stress is easy, because you can test for them regularly, you can do it easily, you can do it quickly, you can have a database. Again, quality control is all about having data. Quality control is not about, oh, I can do it today, I just did something, it came out well, I'm going. No, it's about keeping the data, making sure that you can be consistent in how you do it. And these kinds of measurements help you consistently make those mixes. And that's why. So, yeah, yes.
We have three parameters. If we are looking at these three parameters, are we basically looking at the buildability and explorability?
No. You are, so basically what you have done is, and that's where we are getting into, what you have done is, I have created a mix, I have characterized this, I have printed it, I have printed a few combinations, I have found these combinations to be good enough to print. And because my materials are not changing, I'm saying that this plastic viscosity, this yield stress, this dynamic yield stress is good enough for me to keep as a baseline. And then that's my starting point. From there, you may tweak, you may do different things to improve upon things, but that's your starting point. I may build up, I may get only 1.5 meters. To get 2.5, what do? I have a starting point now from which I change to get to my different buildability.
I but see, we have something to learn from the conventional concrete where we evolved in design process where ultimately we use to design concrete on the functionality.
Correct.
So can't we learn from that? And I don't know if there is any round robin exercise going on, whether there is going on, and number of exercises. I just want to know.
So there are round robin exercises going on for basically not much on the workability things, because everybody, like I said, all printing is dependent not on the material but on the printer too. So when you do round robin, how do you really standardize everything? The cobalt printer is different from an icon printer, is different from somebody else's printer. So what they do is this very generic terms like plastic viscosity, yield stress, you can quantify that. And then for the typical printer, how much of extrusion pressure do they apply? What is the length that it travels through the nozzle? What is the shearing action of your screw extruder? Based on all of that, you make changes, you make these changes accordingly. So you can't generalize it that much, but you can definitely start from a certain starting point. That's where all these tests do. So none of this will take you to the final point, but it will take you to a landing station from which you can play around and get your own mixes. And I think as long as printers are of different families and types, that's pretty much the best you can get to. And what you eventually will do is, of course, you will standardize your mechanical properties, your final performance differently, because that's your eventual thing. But from a workability, rheology point of view and buildability point of view, it has to be a printer dependent thing. Does it? Okay.
Sir,
yes.
I have some with me, sir, very helpful. But I can reject the paste for in a sense for the plastic is cost because there is a magnetic.
Yes. Good question. Good question. So if you measure this for paste and you do the printing, you can relate the buildability and the extrudability to the properties of paste, assuming aggregates to be a dilutant to the properties. Hmm? So you can use the paste qualities. You can do, so I have a plastic viscosity of the paste that goes in because I really can't measure the concrete. You have concrete rheometers available, but it's very difficult. The variability in concrete viscosity measurements are extremely high. So you do the paste measurements, you do your concrete mix or a mortar mix, and you can do mortar rheology too. Not that difficult. All these measurements you can do on mortar sands also. But if you want to do concretes, you can do this mortar rheology. You can actually do the printing of it and see how the rheological parameters relate to it. You will have to do a few trial and error exercises to match it. But once you match it, you have a baseline to start. But otherwise, you really can't do it. Now, the other way some people say is that, no problem, I will give you models to do this. But rheological models, which we will talk tomorrow or day after, are also kind of a hit or miss thing, right? But there is no way that none of this will work without you doing trials. And with 3D printing, you have to do trials with the printer that you're printing with. I do a trial in a lab in my little desktop printer and I take it to the field. Yes, the yield stress in my lab mix was 80 Pascal. And I go and that 80 Pascal paste, when combined with those aggregates, and I tried, I got a workable mix. You can keep that as a standard reference, but you can never say that that's a yield stress of that paste, that concrete. It's a different value, right? So again, it's complicated. It is confusing. It will be like that because we really can't have one measure that goes into the entire spectrum. And that's where knowledge and understanding of what is yield stress, what is viscosity, how can you change it. So if you know that I am able to extrude, but I am not able to build up. Think about a case, right? I did this measurements in the lab. I got a yield stress of 80 pascals, a viscosity of say 300 centipoise, whatever that number is. I did that. Now, who is that? Uh, okay. So if you get that, if you have a plastic viscosity and yield stress that you have from your paste, and you're able to print that in a certain way or extrude that in a certain way, but you're not able to build up beyond layer 5. What does that tell you? What does that tell you? What should I change? Maybe the yield stress has to be changed, right? I'm not having enough. Now, you can also look at what yield stress, dynamic or static? Question to be asked. Maybe both, maybe not, right? But then if it is not building up, it is actually giving you some questions as to why this space is not able to hold its shape and able to hold its weight. You have to adjust some rheological parameters. How do you do that? Again, that is purely in the realm of you as engineers. You might choose to say that I can do it with my binder change. I don't want to do anything else. I just want to change my binder and I can do it. Or you say that maybe my sand content is not enough. I may have to increase the sand because sand comes with some stiffness already. So increasing the sand content automatically increases the stiffness of your mix, right? And then, but increasing the sand might play around with your extrudability. So again, the point is that there is no one size fits all solution here. You have to understand the lay of the land, understand what these basic parameters are, and build up your understanding based on that and be able to do it. Like I said, what you did with one printer could be a good starting point for another printer. You may have to be. I mean, it might work beautifully well. Who knows, right? It might, you did in one printer, you take it another printer, you're able to work wonderfully well. Who knows? Great. If that happens, you save a lot of time and energy. If that doesn't, you have the tools to change things. That's the whole idea. You have to know what to change. Okay. So, straightforward answers. What should I change? None of us can say what should you change without seeing the mix and without being able to go to the field and actually see what is happening. And once you see it, you might say, okay, it is extruding, it is building 4 layers. I need to build to 8 layers. What do I need? Maybe I need to change my sand volume fraction from 0.45 to 0.55. Or I need to change my water cement ratio from X to this. It's extruding so well. I don't need to extrude it so well. Hey, maybe I can reduce the amount of admixtures. Correct? All of those are decisions that an engineer makes in the field. And I use this example. If you're a surgeon operating on a patient, you have all the data that you have. You have done CT scans, MRI scans. This is what it is. He is going to go and open. Do you think that's exactly what he is going to find when he opens the body? You might find something else. The surgeon must be able to act on its feet and say, okay, this was not seen in the CT scan, this was not seen in the MRI, but I'm actually seeing it now. He can't say that, look, I did not see it in the MRI, so this must not be there. It's false. No. At that point, what you see, you should be able to make the changes. And that's what makes a good surgeon different from a YouTube learned surgeon. Right? So that's the whole idea. We'll stop now. So this is, I think this is almost done. I probably have, yeah, um, connections with all of this. We'll start with this again. Going back to the same, answering many of your questions here. It's going back to the same thing. We'll come back after lunch and probably finish this up. Any questions? Any clarifications?
The yield stress that you have mentioned, like, again, it depends on the type of technical, like another amusement patterns.
Yes. Yeah, yeah. It depends on whether you're measuring a parallel plate or a cone. But the character, that's why the protocols that you talked about yesterday, you have to have those protocols lined up and be able to say the yield stress I measured using this technique under these conditions is corresponding to whatever it is. It has to be really, I mean, otherwise, what are we trying to do? We are trying to reduce the number of trials and errors, and we are trying to make sure that scientifically what we are doing is correct so that we can translate it as fast as possible. If you don't have those protocols lined up and if those are not correct, you may have to do extra results to do extra tests to do all of that. Other questions?
Like the cement as it hydrates, its volume is going to.
Yeah.
So, does it not affect the overall packaging?
So every packing calculation is based on the unhydrated state. Is based on water hasn't touched it. So it's all a dry packing. But what you do is you can do it in two ways. You can take a certain volume and say, pack me the best to this volume. Okay. So that is what you typically do to get you the maximum packing fraction. Now, if you want to do post post factum analysis, I have a water cement ratio of 0.4. I used a cement of this particle size distribution. Tell me what the packing fraction is. At that point, you take a volume and say zero point 0.4 water cement ratio corresponding to volume. Find out what that water cement ratio. You say that volume is unfilled. How will I fill the remaining volume? If I have that much of cement, how will that fill the remaining volume? So that becomes so in hydration studies, that's a model that we use because hydration is always with respect to a certain water cement ratio. Whereas for particle packing, to understand what's a maximum packing fraction, we'll just say, here is my volume. Tell me how much is a max I can pack, because the lower the water, the better. Especially for UHPC, my water cement ratio is 0.18. Right? So I want as much packing as possible. Even then, remember, as much packing as possible will still get me only 0.75, 0.76. I have 25% void while my water is only 0.18. What will I fill the remaining with? Right? That's a challenge. If you want a higher strength, I want to actually pack it with something as much as possible. And when I know that I have only 0.18 of water, I want really, really low amount of other stuff. Right? All right. Anything else? If not, we'll come back and continue this. Thank you.